meeting so far has been tremendously illuminating for me. So I have a strange title. So to understand the title, the soft capricious matter part of it, let's look at this micrograph of something which happens to be cornstarch suspension. So the kinds of systems that I have been interested in understanding the collective behavior of are collections of particles like this. So the problem this kind of system poses is that if let me just make you look at just these two particles. Even if I take these two specific particles, imagine they're suspended in a fluid and the fluid is making them move, rotate, etc. At this point in time when the snapshot is taken, the particles are touching at this point and they have some forces acting on each other. As soon as they move or rotate, those forces are going to change. And this is just two particles. Every particle, because these are macroscopic particles, they have, I used to have a scale bar here. So these are more than micron sized particles, like 10, 20 micron sized particles. Because they're macroscopic, these particles have attributes that we normally don't think of when we are thinking of collections of particles like atoms and molecules. So each particle is distinct, they have a shape, they have a surface, so the interactions between them are hugely complicated. And one can try and model them in terms of forces acting between them by putting in some kind of friction coefficient, but I actually don't even know how to model friction between things. One can go to like microscopic structures and say, oh, the surface looks like this, so this is what the interaction looks like. So maybe we start to think of these systems in a slightly different way. And so that's the perspective that you'll hear from me today. But before I talk about, before I go into that, this work has been in collaboration with a bunch of people, Shubhra Bhattacharya at ICTS, Kabir Ramola at TCIS Hyderabad, Itai Cohen at Cornell, Jeff Morris, who is at City College, and Xiaoming Mao, Michigan, Emanuela Delgado at Georgetown. So I have benefited tremendously from the collaborations, and you'll hear some parts of, not all of the work is what you're going to hear about, some of it. Currently, the people at Brandeis who have been contributing to this work is this amazing undergraduate who just graduated, Albert Countryman, and Konaya, who some of you know, was at ICTS as a graduate student with me. Mike Dion was a graduate student. Jishnu was a graduate student. Now he's back in India. Okay, so I want to understand the collective behavior of particles like this, and the reason for me calling these noisy interactions is precisely what I sort of tried to say in words, that you don't know what the interactions are. And this is something Jean-Philippe Bouchot many years ago said, that there's a kind of noise in these kinds of systems which is not just statistical noise, we don't know the interactions well, so what do we do with them? So one aspect of the collective behavior that is very important to understand in these systems is the rigidity to flow transition, the jamming, unjamming transition. So when are they rigid? Why do they form a solid? Like these cornstarch suspensions don't even have any attractive interaction between the particles. So why would they even form a solid? When do they flow? When do they stop flowing? So the basic question that motivates us is, how do we construct statistical field theories for systems like this, sort of close to their rigidity transition? So I'm not going to talk about all aspects of their collective behavior, but close to the rigidity transition. So as I've already said, and maybe it wasn't obvious, but these systems, they are large enough that there's no Brownian motion. Thermal noise is completely irrelevant for these systems. So non-Brownian, noisy interactions. So the approach that we have taken, sort of the the conceit of that approach is that these systems navigate a constraint landscape. So instead of a free energy landscape, it's a constraint landscape. And the particular constraints that we are thinking about are those of mechanical equilibrium. So these things, the suspensions, even if they're flowing, instantaneously the force and torque balances are satisfied. They might be flowing due to external forces, and also these systems will not do anything until I drive them with some external force. So if I put a bunch of cornstarch particles on this stage or put sand grains or whatever, they don't move by themselves. There's no, unless I do something to them, they stay in one particular configuration. So the exploration of phase space is also only through driving. So we start from this notion that can we understand the collective behavior of these systems by saying that systems, we shouldn't think of interactions, but we should think of the collective behavior as emerging from them satisfying the constraints, some set of constraints. And then the other part of what we are thinking in constructing a theoretical framework is the force-bearing networks that can support external stresses and in response to them either flow or stay rigid, emerge in response to external forces. There is no solid, there's no force-bearing network present if I don't have any external stresses. So then what I'm going to show you in this talk today is that these constraints can lead to conserved quantities. This is not a new notion. It's very well known in some parts of physics. We haven't used it maybe so much in this kind of non-equilibrium soft matter physics. So again, this is a non-equilibrium system. You've probably been hearing over the course of the last 2 days that one of the challenges of non-equilibrium systems is what is the distribution. So once you have a conserved quantity, then there is a natural, in these systems at least, there's a natural ensemble that emerges, which is a kind of a microcanonical ensemble satisfying this constraint. And this, for people in the granular glassy community, is the Edwards ensemble. Here you'll see it emerging from a much more basic concept than we have usually discussed in the community. So that, I think, was my last thing. So a natural ensemble emerges from this conservation principle. So before I go into talking about what is this theoretical framework that we have, let me give you some examples of the kinds of systems that I'm thinking about. So where I started from are granular systems. So this on the left-hand side, and someone said this, I don't remember who, I think it was Sunil who said he didn't want to use the word jammed because he would get shouted down. I use a very specific definition of jammed or jamming, and that was introduced in this paper in 1998 by Cates, Whitmar, Bouchot, and Claudin. Jammed systems are whose solidity emerges from the applied stress itself. So there is no solid without applied stress. So that immediately tells me that there is no stress-free solid ever, unlike the normal kinds of things that we talk about. There is no stress-free solid. And the real space network is therefore not predetermined. The real space network emerges from the stresses you put on the solid. And so there is, unlike standard elasticity theory, there's no constitutive relation between stress and strain because I don't even know how to define strain, and I'll get more into that, because there's no stress-free reference state. So there are multiple pre-stress states that are all equivalent in some way. So to show you some examples of pre-stress states, these are images taken with photoelastic beads from Bob Berenger's lab way back. And what you're seeing here is a two-dimensional bunch of particles. The particles are very difficult to see, but it's a dense assembly of particles. You can think of it as a kind of a sand pile, but it's just a rectangular sand pile. There are boundaries at the left and right. And what you're seeing is, because these are photoelastic, the light areas is where the forces are large, and the dark areas are where the forces are very, very small. So as you can imagine, if I just look at this is under gravity. Of course, there's more mass at the bottom, and it sort of looks like the Q model that Satya came up with many, many years ago. So you can come up with models like this. So this is this well-known notion, or a notion which has a kind of mysticism associated with it, called force chains. And what this image is taking this system and then putting a small external force on top of it. And this is what happens after that. And these two images at the bottom is just the response itself. So I subtract A from B. So you see this classic propagation under gravity of the forces. And what I will convince you by the end of the talk is it actually comes very naturally once you think of the system in terms of this conserved quantities and the constraints. So natural response and correlation functions have this structure. On the right here, I'm showing you a system that I'm not going to talk about at all in this, but it sort of, again, is very illustrative of the stress-induced jammed structures. And this is actually experiments in the cornstarch suspension, the image of which I showed you before. And what you're seeing here is a phase diagram. This is the packing fraction, so the fraction of suspended particles in just normal liquid. I think this is glycerol and cornstarch. And this is an implied shear stress. So what you're seeing here, and ignore the DST for now, but they undergo this interesting phenomena of shear thickening. But if you look at this region, the red region is where the suspension is jammed, it cannot flow. In this whole blue region, it can flow. So now, if I am sitting up here, let's say, at high stresses, if I reduce the stress at a given density, it will start flowing, which is sort of weird if you think in terms of elastic systems, because normally we think you have a system which is rigid at zero shear stress, and then if you applied a lot of shear stress, it will yield or fail. This is sort of the opposite that you need the stress to keep it jammed. And the reason I was asking Ludo about whether the tau p is relevant or not is that in this system, we have now shown clearly that this sort of zero shear stress jamming point is singular. The stress is a relevant perturbation because it introduces friction between particles. So this is a frictionless jamming point, and as soon as I go to a non-zero stress, there is some friction, and we have actually now shown that that's a relevant perturbation. But that's a story that I'm not going to talk about today. But this is a flowing to jamming to flowing unjammed transition that you see around here. Okay, there are many more examples that I can think about. I wanted to quickly show this one. I wanted to come up with examples where people actually have thought about the system in terms of constraint satisfaction. And this is tissue remodeling. Actually, this is a collaboration between experimentalists and theorists, Boris Scheinman's group at Santa Barbara. And they come from this, so the tissue flows. And they're asking the question of how does this tissue flow? It's so dense. And their, again, conceit or their approach is to say, it's an active solid that's undergoing plasticity, plastic flow, but the plastic flow is completely determined by the constraints of force balance. So whatever geometrical rearrangement is taking place here, where the cells rearrange, is actually just to satisfy the constraints of force balance. And they have actually come up with a complete dynamical theory to explain this kind of tissue remodeling using this force balance idea. One more sort of active system, which is people have actually, in the active matter community, haven't thought about so much, is solidification due to active stresses. So this is from my former colleague and student, Zvonimir Dojic's lab in Santa Barbara. And what they have is a passive network, it doesn't matter what it is, and an active network of fibers, long fibers. And this active network, when they turn on the activity, a very weakly cross-linked passive network, which wasn't a solid, can actually become a solid. So again, that solid doesn't exist without these active stresses. Okay, so much for giving you examples. Oh no, I have one more. Sorry, because I'm going to talk about this. So this is gels. And gels have this property that they become solid at very low concentrations because there's actually attractive interactions between the particles. So my collaborator and friend Emanuela Delgado studies these gels, and what they noticed is the kind of network that forms can depend not only just the density but also the protocol they use to create these. So these two gels are exactly like the same density, but this one was a faster quench rate than this one. And these viscoelastic properties change with that. So what I'm going to show you by the end of the talk is that there is an interesting connection between the continuum theory that we will talk about, mostly talk about today, and the kind of networks that form here. So this is a rigid floppy transition, again, the same kind of. So the other thing I need for you guys to sort of be aware of and think through is that these systems, I'm saying they satisfy constraints, and there are lots of constraints. They're highly constrained, and I haven't told you yet what the constraints are. So the constraints, let's say in the gels, are at another configuration. In the previous example of the photoelastic beads, if I repeat the experiment, I'll get a different configuration. So we have this highly constrained by highly degenerate set of states. So I need to come up with some ensemble. I need to come up with some kind of way of thinking about how to ensemble average, how to think of these systems. Compared to the traditional paradigm of elasticity theory or rigidity. So the way we are going to think about it is it's a highly constrained system. There are lots of configurations. When do, as an ensemble, these configurations behave as a solid? Or in the flowing system, I'm exploring phase space through the flow. When do they stop flowing and they become jammed? The traditional paradigm of rigidity comes from broken symmetry, right? So even though classical theory of elasticity is very old, we know now the rigidity comes from breaking a continuous translational symmetry. So crystals break symmetry, crystals have a particular pattern that they prefer, so that's how, and they have phonons which are Goldstone modes, so that's where rigidity comes from. Even thinking about it macroscopically from a continuum perspective, what is really fundamental in the standard way of thinking about rigidity is strain. So I have some reference structure, which is, let's say, a square here. I have distorted it, and the distortion I represent by a strain tensor. The strain tensor is constructed from displacement fields, which are vectors from, like every point here gets displaced. So that's this displacement field. So strain is fundamental. And strain is fundamental and has this structure. That tells me, this might be a weird notation, but think of it as a double curl and a curl. of the strain tensor has to be 0. So this is something that's known in elasticity theory and is known as the compatibility relation. So strain is fundamental, it has these properties, and then there's a notion of stress which is derived. So stress is derived by taking the derivative of a free energy with respect to the strain tensor, and momentum conservation of course applies, and momentum conservation in this case, in these cases, is just the divergence of the stress tensor is whatever the external force is. There is no del T of momentum here. And then if in linear elasticity theory, we say linear response, so there's an elastic modulus that connects the stress to the strain. So if I now want to determine the stress state of this system, so I want to know the field, the stress field everywhere, I have enough equations. I have this equation. So in 2 dimensions, my stress tensor has 3 independent components because the stress tensor is symmetric. So I have 2 equations here. But then I have to use this equation. I have to use this equation in combination with that equation, and that gives me enough equations to solve for the stress state. This is not something we explicitly talk about sometimes because we just assume elasticity theory, but I need this. I need this. Without that, I cannot solve for the stress state of the system. So for the rest of the talk, what I'm going to do is ask, can I come up with a set of equations which lets me solve for the stress state of the system when I have no notion of strain? So I cannot connect to strain. Is there a stress-only formulation of rigidity or elasticity theory? That's going to be the bulk of my talk. This one? So this one, in 2 dimensions, it's just enough. In 3 dimensions, you can take any of them. It's overdetermined. But if you don't have this, then you absolutely don't have enough. And you'll see that in the way we come up with it we map a different theory onto the stress problem. In that theory also there's this overdetermination problem. Okay, so the next thing I think I'm going to skip, just wanted to say that the plasticity in normal elasticity comes from violation of this condition. So in crystals, when we talk about defects like disclinations and dislocations, this is non-zero. And in amorphous systems, there has been a search for similar defects by, again, asking when is this compatibility relation violated. Okay, so the next slide I think I can skip, but basically what I am now looking for is, can I have a stress-only formulation of elasticity theory? Can I come up with a stress compatibility relation without relying on strain, ever? So to do this, I need to introduce this idea that constraints can give rise to conservation laws. And to do that, I'm going to use a model. So you should turn off basically trying to understand the microscopics of the model that I'm going to just flash before you in the next slide. The microscopics comes from a very different system, but the notion that's illustrated in there will be very important for us. So what I'm trying to do here is get you used to this idea that constraints can give rise to conservation laws of a kind that we are used to in other parts of physics, but not so much in soft matter physics. So this system, what I have drawn here, for people who know this system, maybe these are some representations of the ground states of the triangularizing antiferromagnet, but that's irrelevant for us. Let's say what I have is a system where I have this honeycomb lattice, and on each bond of this lattice, I can either have 2 arrows pointing, let's say here, pointing up, and 1 arrow pointing outwards. So 2 arrows coming inwards into this vertex, 2 arrows going outwards. And I have the constraint that at every vertex, this has to add up to 0. So if 2 are coming in, 2 have to go out. I cannot put 2 here. Then that violates the constraints. But I can put them in any order here. But at every vertex, I have to satisfy this constraint. And so this is one possible state that I can have. This is another possible state that I can have, which is actually ordered. All of these 2 arrows are in the vertical direction. One thing that comes from this constraint, which might not be so obvious, is if I now add up, let's say the total, if I think of this as a current or a flux of an E field, an electric field, that's how we're going to think about it. If I think about what's the flux of the E field in the vertical direction, so if I look at this row, there's 4 going up, 2 coming down, so there's 2 net. Every row has to have 2. I cannot change it. So there's a local conservation that propagates through the system. So then you can understand that the only way I can change this number 2 is by doing something at the boundary. Or I can violate the constraint. But if I'm not allowed to violate the constraint, I cannot change this. So in this one I have 2. In this one you have the maximal flux. So every maximal vertical flux. And so the number of configurations that satisfy this total flux condition, in addition to this local constraint that every configuration has to have, depends on what is this total vertical flux. So here I can only have 3, right? I only have 1 if I say the vertical flux has to be this. So the way to construct continuum theories for models like this has been explored. I don't want to say explode to death, but explored heavily in the community of classical spin liquids. And what you do is you say, okay, this field, let's say these are these lattice sort of E fields whose fluxes have to add up to 0, that tells me that I have a Gauss's law. I have a divergence of E is equal to 0 at every point. So the continuum theory is just built upon this Gauss's law. And if I just want to look at the static configuration, the ensemble properties of the static systems, then I actually write down a free energy which looks exactly like the electrostatic Lagrangian with the E square. And there's a stiffness here which depends on which flux sector I'm in. So the stiffness depends on whether I'm here or here. And there's a natural ensemble associated with it, which is that all states that satisfy the constraints are equally likely. And the reason is there is nothing else that distinguishes them. All of these configurations should be treated in exactly the same way. How many minutes do I have? 10? 5 minutes in question? I have only 10 minutes left? Okay. Okay, so I'm going to go quickly. Okay, so I'm going to quickly, this is just going to be a mapping. So now I'm going to look at jammed solids, let's say the granular solids, and I'm going to think of it in this kind of paradigm, that's a constraint satisfaction problem, and that these solids don't exist unless I have external forces. So let's imagine I have external forces which are just pressure, and then there are contact forces that develop between grains inside this. This system now satisfies constraints, which is force and torque balance, right, at every point. So think of this as analogous to satisfying that divergence of E equal to 0 in my previous system. So this is just divergence of this coarse grain will give me a divergence of sigma equal to 0. This will give me sigma is symmetric, but this is another conservation law. So the question is, and I'm going to skip quickly to that. So in the previous problem, I had charge is conserved, right? I had Gauss's law, divergence of E is 0, so charge is conserved. In this system that I'm thinking about, I have two conserved quantities, And the question is there an ENM-like framework which has two such conserved quantities? Is there a gauge theory which has two such conserved quantities? If there is, then I'm basically done. And then I'm going to just show you results. So the hard work was done for us in 2018, and this is how all of this, well, the story started long ago when Silke was a graduate student with me, but the closure to this theory came because I was talking at ICTS and Shubro told me about this theory. So this theory, and you can ignore this side of it, but there are, in 2018 or even earlier, people had been trying to develop these tensor gauge theories, which are U1 gauge theories, just like a normal ENM. But here, the E and B fields are symmetric tensors. They are not higher form gauge theories for the experts in the audience. They're symmetric tensors. And there can be two kinds of Gauss's law for these symmetric tensors. We're going to ignore this one. This is the one with the vector charge. So very simply then, what do I have? If I just simply mapped the E tensor to my stress tensor and the charges, which are here vectors, to my forces, I have the divergence of sigma equal to force or divergence of sigma equal to 0, Gauss's law. So we can just go ahead and develop this. This tensor gauge theory has these four Maxwell's equations. If I look just at the electrostatic version of it, which is just the left-hand side, then what do I get? I get divergence of E is the force, and I get this compatibility equation because in the static, the right-hand side is 0. There's no current and there's no B field. So I get a compatibility relation for the stress. There is no strain involved in here. And then we just have to do a little more work, which I'm going to so just to make it clear, then this theory actually has these two conservation laws, which are these two conservation laws for me. And the reason this has been interesting in the spin liquid community is these two conservation laws highly restrict the way charges propagate. So because I'm running out of time, I'm quickly going to go into that. Yes? It can be, in this theory, you can have magnetic monopoles because it's not a real ENM theory. I haven't talked about the magnetic field at all because it doesn't show up unless I think about dynamics, or equivalently, I can think of this F. The stress tensor is like an electric displacement field, like if you have a polarizable medium, and the E field is like the normal E field. And I don't know how to measure that. So the stress is this, but this is the E field, and that's the one that satisfies a compatibility relation. It's not strain. These phi's are not displacement fields. They are just gauge potentials because my E field satisfies this condition. So it's completely, the reason for the compatibility relation is not because I derive something from a displacement field, but because in the static limit, I have to satisfy this condition. So basically, that's the story. I'm just going to quickly show you 5 minutes into questions. I'm already into questions? Yes, okay. So this is quick. So these are just, this is 2020, 2022, but these are predictions of the theory about stress correlations. So it's a field theory. It predicts stress correlations given some coupling constants, but we can extract the elastic moduli by fitting numerical or experimental measured correlations to the theory. So that's something that we've done. But I wanted to quickly show you what force chains are. Force chains, so these three configurations, these three pictures that you see are actually exactly the same configuration. And you would see in this one, I'm seeing force chains in the horizontal, force chains in the vertical, force chains along the diagonal. What these experimentalists, Jie Zhang and Inchio, did was they colored the grains by the x component of the stress. This is colored by the yy component, and this is colored by the xy component. So what we see as force chains is a property of the stress correlations, and the stress correlations are highly anisotropic. So the longitudinal correlations and the transverse correlations, so the longitudinal correlations are positive and extend, and they are power law. The transverse correlations are also power law, but they're negative. So this is what's basically going on in force chains. Okay, so that's the end of the story, and I know that, so I just wanted to show you we can calculate the response, and the same thing happens. I'm going to completely skip all of the gels that I wanted to talk about and go to my summary. Okay, so let me just put up my summary and then thank you all.
So can you explain what the gauge theory, gauge field is? So how to detect the gauge field in your, which you introduce phi I and phi j. So you should connect such field with an observable. Like
how do I connect a potential to an observable?
Yeah, but the AB
that.
effect, you know, can be connected to the original vector potential, which is so
this is not a vector potential. This is the analog of the electrostatic potential.
Yeah, I know that. So you should explain the connection between the real field and the real gauge field.
Real field and a real gauge field. I don't know how to do that, but I can tell you that if you say that I am looking at two configurations, and I will just say my potential is 0 in this configuration, and then you ask what the displacements are of the particles from this configuration to that configuration, that will show up as your electrostatic potential. So basically what we are saying is there's no notion of a unique reference state. So if I now ensemble average, there's no notion of a displacement field. Yeah. But I can always fix the gauge for one. I can just say the electrostatic potential is 0 for this configuration, and then I can measure potential differences. I cannot measure the absolute potential. And there's no Aharonov-Bohm effect that we have figured out yet.
Yeah.
That's it. Yeah.
So recently I heard a talk by Anil Lamaitre who he talked about stress correlation.
Can I just say something, and Anil will agree to this? He has a mathematical formalism.
Right.
So
but maybe
if I say divergence of stress is 0, then the stress tensor can be written in terms of a potential, which is known as the Airy stress function. So if you know the Airy stress function correlations, you can figure out all of the stress correlations. This is what Anil does in a very complicated way, because he says if I measure one correlation function, I can measure the others. But by measuring that one stress correlation function, he is figuring out what the Airy stress function correlation is. So if I know the Airy stress function correlations, I can work everything else out. It's writing the stress in terms of a potential. He doesn't have a theory for why the Airy stress functions have to have that correlation. But I have a Lagrangian. I can give you all of the correlations of the, I write the Lagrangian in terms of a potential. There is no unknown in here.
You have two conservation laws, right? So and you're using the Edwards-Hahn symbol where all the things are equally likely, basically. But in general, if you have, let's say you have n conservation laws,
yes,
you can use this GG or something, generalized Gibbs-Hahn symbol that you use one Lagrange particular for each of the conservation laws.
Yes.
So how does, if one does, is it necessary to do it here or not necessary?
You mean to how do I incorporate the two conservation laws? Is this what you're?
Conservation laws. You can
are you saying more?
In many ways. So one.
No, right. But here there is a more basic thing. Is I have a Gauss's law. Yeah. I have charge conservation. So basically everything is incorporated in the fact that I have vector charges, and these vector charges have to be conserved, and they're, because the fields are symmetric, then the charge angular momentum also needs to be conserved.
Okay,
So it's a more basic charge, there's a physical sort of charge conservation embedded in there. So that's it comes very naturally, yeah. Yes, it's microcanonical because if I say that everything is just determined by constraints, then every configuration that satisfies those constraints are equally likely. And the theory only emerges after I do that ensemble average. The continuum theory is an ensemble average theory.
Okay, perhaps we can move on to the next speaker. We're a little bit late.
Oh, there's one.
Okay, well, Shiva,
Thank you.
we move.
My question is if there is an intuition behind the stress compatibility condition, because when we talk about the strain compatibility, we talk that the displacement field, it should be sufficiently smooth and there should be no discontinuity in the displacement
Right.
fields.
So it's a very different intuition here, and I didn't get to talk about it. So if you violate the stress compatibility relation in normal elasticity, that's a defect. The only way I can violate the stress compatibility relation here is by introducing a B field, which means I immediately have dynamics. So that's actually a very appealing picture to me, that in these kinds of solids, if I violate compatibility, the system will immediately flow. There is no way of supporting a static defect structure, unlike the strain compatibility. So that's not an intuition, that's math, but that's the difference.
Sriram doesn't need Tell me 10 minutes before the end. Yeah. Oh, that's what you said. Yeah. Okay, fine. Okay.
Okay.
All right.
Now, go. Our next speaker is Sri. Thank you so much.
Thank you. So let me begin by thanking Pinaki and Arnab for planning this meeting. As other speakers mentioned, there have been earlier times when one came regularly to Chennai, and that has been a little slow of late. And so I appreciate the effort to sort of revive traffic in Chennai. So with that, so I'm going to tell you today about a part of work that we've been involved in for quite a while now on cyclically sheared glasses. As an aside, several years ago, I was talking to a colleague who was doing granular matter in rotating drums. And so the first time I met him, he told me about this. And the second time I met him, so I asked, so what are you doing? And he said, you know, the same rotating drums. And I said, so you're going around in cycles, are you? So many years later, I've been doing the same for the last 10 years or so, looking at glasses under cyclic shear. But today, I won't talk about stuff that, hopefully I won't talk about things that many of you have heard at least more than a couple of times. But before I get going, so this is sort of, like I said, work that's been done over some years with several, broadly what I'm going to be talking about, concerns mechanical behavior of amorphous solids. So solids exhibit stresses involving plasticity and eventually failure, and understanding failure is of obvious importance for a variety of materials. So a lot of what we do know as textbook material concerns crystalline solids, but and part of the reason is that they are a large part of solid materials that we study and use, but amorphous solids arguably has a much broader diversity of contexts in which it appears, both the amorphous solids themselves as well as the failure of these solids as a matter of interest or concern. Okay, so that's supposed to be illustrated by all these different examples, including hard glasses and soft solids and so on. Okay, a particular problem that we have been sort of trying to focus on lately is illustrated this video of something that we've all done many times, which is if I were to try and break a solid, I usually can't do it in one go. So what I do is to sort of go back and forth several times, and there's some, depending on how hard I'm bending back and forth, there's a certain number of repetitions after which the material breaks. Okay, and this is something that happens because of changes in the internal structure of the solid that is not visible to the outside very easily, and this is something that historically wasn't well appreciated in the early part of the industrial era, and the lack of understanding that fatigue as a phenomenon can happen when a solid is subjected to repeated load, led to various disasters in the middle of the 19th century, including this famous rail accident in 1842, which made people wake up and pay attention. And like I said, since then, the problem of fatigue and fatigue failure has been extensively investigated and empirically sort of studied, and without commenting more about how well it is understood in crystalline solids, what I would like to sort of state without further discussion is it appears as though for amorphous solids the same phenomenon has a different character. Okay, and this is a reason why one should be interested, and we have been interested, and I'll tell you a little bit about that as we go on. But before moving on from this slide, here is sort of a representation of this phenomenology where, depending on the amplitude of the stress that I'm applying, there are different numbers of cycles after which failure occurs, and this is represented in something called the SN curve. So the cycles to failure on the x-axis is a decreasing, okay. As stress decreases, the number of cycles increases. Below a certain limiting value of the stress amplitude, one may in fact subject the system to the solid to stress indefinitely without failure occurring, right? So this limit stress is called the fatigue limit, and this is going to come up later on. Okay, so now if we look at, okay, so what we do is to look at model amorphous solids under cyclic shear, and okay, so a lot of the work that we have done has been to look at numerical simulations of model glasses. I won't focus on this part of the work, though I will mention some results by way of background. But we've been sort of also trying to build simplified descriptions in order to identify salient features. And so one set of such works has been looking at simplified what I call single site models of plasticity, and what that means will come up in a minute, and then corresponding mean field theory to understand sort of yielding and failure, but also there is another set of work where we look at models which have spatial extent and interactions across space are a relevant part of the description, and these go by the name of elastoplastic models, and I'll show some results from these elastoplastic models. And as I go through the next few slides, what we're going to be trying to do is to sort of follow this dictum which is attributed to Einstein, that everything should be made as simple as possible but not simpler. And so we're going to sort of go from one simple description to a simpler description and see how far we can keep going without becoming trivial, right? Okay. So, so here I won't say too much because this is really not what I'm going to be spending much time on, but we do simulations of cyclically sheared glasses, and what I show here is what we are doing. We take local energy minimum configurations which are obtained by subjecting equilibrated liquid configurations at a temperature called the parent temperature instantaneously. So you have energy minimum configurations, but because of the initial liquid configuration and at what temperature it was equilibrated, for each parent temperature, the glass that you generate this way exhibits a different degree of annealing, right? So if I equilibrate the liquid at a lower temperature and then do a local energy minimization, I have what I call a better annealed glass. Whereas if I start from a high temperature liquid and do a local energy minimization to obtain my model glasses, I have what I call a poorly annealed glass, okay, just to set the terminology. And then such glasses are subjected to either what's called athermal quasi-static shear, with no temperatures involved, or finite temperature, finite shear rate simulations. And in each case, we typically look at the properties of the system at the end of each cycle. And because there are plastic rearrangements, the properties of the system change from one cycle to the next, okay, till some steady state is reached. Okay, so this is one set of results for athermal quasi-static shear, where basically the summary of what I'm going to show you in steps is that the energy per particle of the system, which is the quantity that we monitor, depends on the strain amplitude and the initial energy when I apply small amplitudes of shear. But for sufficiently large amplitudes of shear, the amplitude by itself determines the final state that I reach. And in between these two regimes, one has the phenomenon of yielding, okay? So this is a small amplitude shear, cycle to cycle, the energy changes and reaches some final value. A larger amplitude will lead to a lower energy being reached, and it takes longer to reach that. And one keeps going till beyond some amplitude of shear, there's a qualitative change in behavior where the energy now begins to go up, okay? And this in this part of the story, depending on whether I start with a poorly annealed glass or a well annealed glass, the behavior is very different, okay? But if I go to larger amplitudes, now I begin to have final states. It's not very obvious from this picture, but I begin to have final states which don't depend on whether I started with a well annealed glass or a poorly annealed glass, but I reach the same final state, okay? All right. Now, this is a larger set of results showing the same thing. As a function of the initial energy of the glass, I have a very different way of going through the yielding transition. For poorly annealed glasses, I have mechanically induced annealing before yielding happens and the energy begins to go up. And as I already mentioned, the number of cycles that I need in order to reach the final state has non-monotonic behavior and an apparent divergence at the yielding transition, and this divergence of timescales when I'm coming from above is associated with the phenomenon of reaching the fatigue limit upon reducing the load. Okay? So the yielding transition, as I'm describing it now, would correspond to what we might call the fatigue limit. Okay? Now, something that was apparent here, but I show here in a much more dramatic way, is if you look at strain amplitudes, which is my control parameter, whose values are such that eventually the system will fail, right? So all of these values that are for which I'm showing results here, if I look at the initial part of what happens for the initial cycles, I have behavior that's very similar to the case where I don't yield. So in other words, with initial cycles of shear, I anneal my system to lower and lower energies, and at some point suddenly I fail. Okay? So the change in the properties of the system are non-monotonic in this very interesting way. Okay? That there is initial mechanically induced annealing followed by failure, and one of the sort of the key questions to understand is why is the process of making a better glass leading to failure eventually, right? So what's the connection between the processes that lead to a better and better annealed glass and then failure happening at some particular time, okay? So, okay. Yeah, so that was that. Yeah, by the way, I sought the help of my students to make some of these slides, and they've made a lot of transitions. I hope is a priori interesting in terms of the structure of these plastic rearrangements. Okay. However, what one does understand is that when there is such a localized plastic in the surrounding solid, and this is something that people have discussed a lot and understand it has 1 over r to the d variation with distance and spatial anisotropy of the form that's shown here. But the basic idea is I can think of my amorphous solid as made up of mesoscopic sized blocks within which I can think of how to describe plasticity. And then anytime when there is a transition that corresponds to a plastic rearrangement in one of these mesoscale blocks, it has consequences in the form of stress propagation to the other blocks. Okay? And this is the reason why I earlier mentioned modeling in terms of a single site and spatially extended elastoplastic models. So if I were to sort of focus just on one of these blocks and try to come up with a description of what happens there, that's a single site description, which ignores what's happening elsewhere in the system, but a complete description would have to include also the manner in which these different blocks talk to each other. Okay. Okay, so now from what I said, it's clear that if I'm sitting at some point in space and asking what are the stress kicks that I'm getting because of what's happening elsewhere in the system, the mechanical noise, well, I'm looking at who else, but including work by Ludovic and I'm not sure about Massimo, but anyway, is that the degree of disorder or stability of the glasses is an important variable, right? So if I think of a small piece of the glass, in addition to sort of asking, you know, how it responds mechanically, or rather in answering how that little block responds mechanically, I have to think in terms of how stable the packing is, okay? So a natural language for this is to think in terms of a distribution of energies that that particular block can be in, such as what a Gaussian distribution of energies, but more importantly, to have something to say about how stable to mechanical stress a given block is based on how low the energy is. Okay, so this is sort of an energy landscape picture of an individual mesoscale block. So I can think of the system residing in different what we call mesostates, which have different energy in a stress-free condition, and then I can sort of change the strain so that the energy goes up quadratically with the strain, and at some point I'll reach a limit of stability, and this limit of stability I choose to be proportional to the square root of the depth. Okay, and when you reach the limit of stability, you hop into another minimum. Okay, that other minimum under athermal conditions would have to be a new mesostate which has at that strain a lower energy. Okay, now if all these parabolae had the minimum at the same strain value, that's one sort of simple situation, but because of plasticity, the stress-free arrangements of atoms can be at a finite strain, right? So the plastic strain that is associated with a stable packing can be arbitrary, and this is also why Bulbul was sort of talking about a stress-only description, because strain is not yeah. So, but anyway, but we are sort of thinking in terms of strain. So the correct description to have in mind is to have states that are possible for the system where the minimum energy can occur at different strain values. Okay, so here, for example, this parabola has a plastic strain that's very different from this green parabola. So at the point when the green or the blue parabola becomes unstable, even though this is a higher energy minimum, I can make a hop down to this because at that strain value, the energy of the system is lower. Okay, so this is now a description of what happens if the system is residing in one of these states, and I change the strain on the system. And with this description, I can sort of then perform the dynamics and look at what happens from cycle to cycle to the energy of the system, just like what I described in the simulations earlier. And one gets a yielding diagram which looks qualitatively very similar to what one sees in simulations. Okay, there are interesting differences, but the basic idea is, but the basic features that are reproduced are when I start with a poorly annealed glass, which is high energy, I have initial annealing before I yield as I ramp up the strain amplitude, whereas if I sit at a very low energy state, I do nothing till I reach some amplitude at which I make a discontinuous jump. Okay, so these are qualitative features of yielding that are reproduced, except for this particular model, this is actually the behavior of the system after a certain number of cycles. There is no genuine transition, okay? Because if you wait long enough, eventually you'll find a minimum which is deep enough and stable enough that you don't then make further transitions out of it. So this sort of reproduction of simulation results is a little bit misleading, okay? But one can build on this as I described and try to do better, but at this stage I'm going to take this already simple-minded model and make it even simpler. Okay, so instead of looking at transitions from one mesostate to the other, as I vary the strain cyclically, I'm going to ask what might happen to the system if I look at it at the end of each cycle stroboscopically, right? And so here is some sort of simulation results for this system where I'm showing the initial energy of the mesostate that I'm occupying on the x-axis and the final energy after a full cycle on the y-axis, okay? And without going into the details, what you can see from the color map is that the final state that I reach at the end of the cycle doesn't seem to depend much on where I started, okay? Because basically, yeah, if I take any cuts here, I get the same distribution that looks like this. And this is sort of an approximate statement. I won't go into the details, but basically what this suggests is that it's useful to think in terms of an invariant distribution that you can, think of the system as occupying. And that invariant distribution in turn, I can think of in terms of a potential, okay? So a useful simplified description is to think of a random walk in a confining potential, okay? So this is what we take up. This finally didn't get fixed, but I'm going to take advantage of the transition problem. So, okay, so here is now the system that I'm going to look at. I have, okay, perfect. I have a random walk in a confining potential, but the axis here is energy, right? So I'm making a random walk in energy space, and then if I'm applying a strain of a certain amplitude, it corresponds to the system being stable only for large enough energies. I've flipped the sign here, so these are deep minima and these are shallow minima. And so for any amplitude of strain, I have a boundary beyond which the system will be stable with respect to a cycle of shear, but for smaller energies, it will make a transition to a new minimum, okay? So I can therefore ask the question, how long does it take the system to reach this threshold, right? So this is now a very standard problem of first passage time, and the answers are known. So there is a time scale which I call the absorbing time, which is growing very strongly as I shift this boundary to further and further to the right. And again, I can take this model and sort of look at what the state of it is as a function of the number of cycles. And again, I get a yielding diagram which looks very similar. And once again, there is no genuine transition, because if I wait long enough, I will eventually get trapped, okay? But the way to sort of have a more realistic and interesting description is to say, even if I am at a sufficiently large or low energy so that I'm stable with respect to a given amplitude of strain, is it possible for the system to escape out of these stable states, the absorbing states? Yeah. Oh, on this side, yeah. Now this is coming from an approximation where you assume that it's yeah. It's a large first passage time result. Yeah. Okay. Okay. So that's what we look at next, which is even if I have this random walker in a confining potential and it reaches an absorbing state, the absorbing state is not permanent. It can escape out of it. Then we have to ask, what is the mechanism for you to escape out of it? And the mechanism is what I mentioned earlier, which is the stress kicks that the system might experience because of activity elsewhere in the solid, okay? So here is an illustration. So if I'm sitting in a minimum state like this, and this is my amplitude of, this is my amplitude of strain. At this point, I'm not quite at the stability limit, but if I imagine that because of stress kicks, I diffuse in strain space, I can eventually reach that limit of stability and make a transition. Now, this diffusion in strain space, I would like to associate a diffusion coefficient to, and what I'm going to say is that this diffusion coefficient is going to be proportional to the fraction of states that are unstable to the given amplitude of strain. Okay? So here, just for concreteness, I have all my energy states, and for a given strain amplitude, this is the boundary between stable and unstable states. And I'm going to ask what is the probability for the system to be in the unstable states, and that probability is going to determine what the diffusion coefficient that I will have, which will allow me to escape out of the absorbing states. Okay? So we can sort of have that picture and write a two-state description where I write the master equation for the unstable probability, the probability to be in the unstable and the stable states, and without going into any detail because I'm running short of time, what this does is instead of making the yielding transition only apparent, it actually it makes the transition a genuine transition, and it also gives you a divergence of timescales like what we see in simulations with some problems. The exponent that comes out is not the same as what we see, but we've made so many simplifications that maybe, you know, it's a little much to expect everything to come out right, but here it is. Now, okay, sorry. Then we said, you know, one thing that this two-state description will not give is any kind of a non-monotonic dependence of the state of the system with respect to the number of cycles, because the description of the system is not rich enough. So we said let's go to the next minimal description, which is to think of a three-level description where I have unstable and stable states, and I also have a new category which is the threshold states. Okay? And then I can write the corresponding dynamical equations, and when you look at the behavior that emerges, what you find is this very interesting behavior where if I look at the population of unstable states and the absorbing states, with the number of cycles, both of them actually diminish, and the population of the threshold states, on the other hand, goes up. So you have stable and unstable states, both of them converge towards the boundary. Okay? And this I can represent in this flow diagram where I have the population of unstable states and the threshold states, and what you see is this initial behavior where PU, the unstable state population, continues to decrease, and for some initial conditions, indeed, I just go to 0. But if I have a large enough PU, after an initial phase where it decreases, it turns around and goes to a fixed point where the unstable state population is finite. And this is behavior that I find when I have yielding in the system for large enough strain amplitudes, and I can sort of look at what happens with respect to the strain amplitude, how the flow of states changes, and this non-monotonic dependence is capturing what we see in simulations in a much more complicated setting, and the fact that I have several initial conditions where even for an amplitude that's greater than the critical amplitude, I can end up with an absorbing state, captures the behavior that we see in simulations of a range of initial conditions for which I don't yield. Okay, so okay, and just 1 minute. That was sort of a schematic set of equations that I wrote, but I can actually construct the same equations for the Ehrenfest model that I discussed earlier, and I get qualitatively the same behavior as the toy model that I wrote just now. Okay, and this I will skip with difficulty. Okay, so elastoplastic models reveal the same behavior of non-monotonic change that we see in simulations. And okay, let me skip this. We do see a divergence of timescales with some interesting details which I can explain. Okay, so that's the summary. So what I've described is a set of ever more simplified descriptions of the dynamics of glasses under cyclic shear, and the most simple of them continues to capture the essential interesting features of the dynamics, and gives us some insight.
Assume that strain didn't exist. Can you come up with a stress-only, extract a stress-only description of plasticity from looking at the simulations?
Right.
Like, why do you need the crutch of strain?
So, no, so the point is, okay, so how I mean, in principle it could be done, I suppose. No, like I said, the one thing that we do try to incorporate in this description is that there is disorder, so that I have different levels.
No, I understand,
right? But then, yeah, then you have to say.
For example, let me ask you, if the plastic strain is not uniquely defined, then is there a stress-strain relation? Like, what's going on?
No, the stress-strain relation is not uniquely defined, but once you fix the plastic strain, it does become uniquely defined. That's the whole point. But that plastic strain is an additional variable in your description.
You're introducing sort of what I would, yeah.
Yeah, but anyway, no, I don't know how to do it with a stress-free way, but this is sort of a construct which takes care of the fact that the strain is not a good variable by itself. Yeah.
Okay, perhaps we will move on to the next speaker. We're a little bit below schedule. Thank you.
Thank you.
You want to waive 3 minutes before the end, something like this?
Yeah, 12 plus 3, right? Yeah, I will try to.
So our next speaker will be Pampa Day, a run and tumble-like motion of a Marangoni swimmer.
Okay. Good afternoon, everyone. I am Pampa from Physics Department, IIT Bombay. First, I would like to thank the organizers for giving me this opportunity to present our work here. Today, I am going to talk about run and tumble-like motion of Marangoni swimmer. It is an experimental-based project. We proposed a simple toy model to validate this system. Also, I would like to thank my supervisor, Professor Puneet Paramananda, and Professor Amitabh Nandi, and my collaborators, Abhishek and Ars, and all of my NLD lab members for their support and system. It is also, people have observed this kind of behavior with a non-living system. This is a recent work where they have used phenolphthalein disc within a Fe2+ solution. And this is also another another non-living system is the Camphor's graph, which shows this linear motion and the circular motion. These two systems work with the Marangoni flow. So in our lab, we designed a Marangoni swimmer which is able to show 3 different states: run, tumble, and the rest states. We are calling it as a Marangoni swimmer. It is camphor infused. Okay. Before going to, why it is not working? So before going into the detail of and the camphor, and we inspired from this paper how to make the camphor pen. So we made different concentration pen, suppose 1 and 1.5 molarity, and then we took A4 size paper and cut this paper as a trapezoidal shape, and this then we have drawn a camphor pattern on it. This is an asymmetrical camphor pattern, and then we put this swimmer, we are calling it a swimmer, so on the flower shaped container which is filled with the water, and started to observe the motion. So this motion it is releasing the camphor on the water and producing the torque. So and the resultant due to releasing of the camphor, it is producing the gradient, surface tension gradient, and the resultant force. If the force comes from the top of the center of mass, it will show the counterclockwise. If it comes from the below of the center of mass, it will show the clockwise, and if it is from the bottom to top, it will show the run. So we have observed that this there is a intrinsic chirality of this system. We have drawn the different pattern which is mirror shaped of the previous one, where the counterclockwise rotation was more prominent. We continued with our system with the first pattern, where the clockwise rotation is more prominent. It is a stochastic process. There is no predictability when which states will occur. Therefore, we characterize our system and categorized into 3 states. There is a translational speed and the rotational speed. We manually put this threshold value for the translational and the angular both. If the angular speed is less than the threshold value, then we consider it as a run state, pure run state. If the translational speed less than the threshold value, we consider it as a tumble state. If both of them are less than the threshold value, we are calling it as a rest state. It is one of the experimental movie where the green vector shows the orientation of the swimmer and the red one is the velocity vector. It will show the run, and then it will show the tumble. When it is tumbling, there is a 90-degree 90-degree angle difference between 2 vectors, velocity and the orientation vector. So these are the snapshot of the 3 states. We have seen that in our system, tumble and the rest states are more frequent compared to the run state, and the consecutive tumble states and the run state and the rest states there is no correlation. This is a return map plot. So we can predict from this plot that the system is stochastic. Our experimental system is stochastic, and this is a residential time statistics plot where the rest and the tumble time is higher than the run state. We defined this as a sigma. Sigma is 0, 1, 2. Then we proposed a simple model to understand the system. We consider it as a chiral active Brownian particle. So there is a switching rate from rest to tumble, tumble to run, and run to rest. So we take the switching rate is considered as the probability between 2 states and the inverse of the multiplication with the inverse of the residential time, what we have calculated from here. And then we put this transition rate into the using the Gillespie algorithm, and we produce the new state from the simulation. and these states we used in the overdamped Langevin equation, and it depending on this, depending on the sigma value, it will show different state motion, and these are the corresponding trajectory. Here we only tune the thermal noise and the rotational diffusion coefficient. We have observed that for smaller value of the rotational and the thermal noise, it matches with our experimental system. Here it is a mean square displacement plot, where we have seen the run time, there is a ballistic motion which within the 1.1 second, and the dip has been observed at the tumble time scale, and this is the exponent plot. To understand the exponent clearly, we have taken the derivative of the MSD, and the diffusion coefficient should be less than the tumble time scale, inverse of the tumble time scale. Okay. So, in summary, this is our experimental trajectory, where we have observed 3-state system, and it is stochastic, and then we proposed a model, a simple toy model, and here is the mean square displacement plot, which shows the different time scale behavior, and this motion is clear before if the time scale, if the simulation time scale for the rotational diffusion should be less than the tumble time scale. So that's it. Thank you.
So much. There's a question over there. Bulbul.
I was unclear to me what made this the particle. What determined the orientation of the particle, the natural? You have that arrow, so
It
where
is
that coming from?
it is the orientation like with respect to the center of mass, like
But because of the shape.
yeah, because of the shape. So in this movie, it is clear, I think.
Okay, I see.
Can you explain the MSD plot once again? Like,
Yeah.
and what are the features of it?
So yeah, I skipped. So it is initially, there is a ballistic motion for a short time scale. There is a slow crossover. I think this slow crossover is coming due to the tumble on the rest state. So first we were confused with this slow crossover, and then we plotted this exponent, and here in this exponent you can see there is a dip. So this dip can be controlled with this parameter lambda. So it is, if you reduce the value of lambda, the tumbling radius will be increased, and the dip of this exponent will change also. It will be more deeper. It will go. So that's the point. I think am I able to address?
Yeah, and is there a reason like why the exponent like goes a bit wild when you look at
It is.
large time?
This is.
Yeah.
It is coming at a fluctuation only.
Okay. Thank you.
The rest motion I understand would be decoupled from like both the run or tumble motion, but in no cases are you seeing running and tumbling together. Like you're defining all three motions as like all three states as entirely separate, and in some sense like if one is happening, another is not happening. It's a succession of run, then tumble, then rest, and then run and tumble. You don't see, it's not possible to see like say run and tumble together, where it's rapidly rotating but also moving like translationally at one point. Is anything preventing that is what I'm asking.
Can you repeat? I don't.
Is there any reason why we should not expect these two events to happen together, for example, these two states to coexist?
Because of this shape, of the swimmer. Because actually, when I have already mentioned that it is releasing camphor, and it is sometimes the gradient forms in such a way it is producing this straight run motion, and it is not in our control, and most of the time it shows the chiral motion, this rotational, but I think the shape is responsible for this. There is no any other reason yeah. Sir.
So in the run state, is it possible for you to just paint the camphor differently and make it run with the fat end forward?
I don't get.
Can the particle run with the fat end forward? Now it's running with the thin end forward.
Yeah.
Can
Can
you?
it go, can you
Can you-
reverse the sign of
Okay. After some time, it can go like okay. So your point is
Can you change the paint?
change
the pattern of the camphor and make it go fat and forward.
Yeah, that depends. Proportionality. It depends on the proportionality of the camphor. If the shape is same, if the gradient, if I draw the pattern in the reverse way, I don't think it can show different motion. I don't know what kind of motion it will show. I can show you one thing. I think that makes it clear. Yeah. So this is a very simple explanation. If I take the rectangular shape and draw the pattern, it will mostly show the force will be balanced from this side, and it will show the straight run. If I start to increase, there is a chance to rotation. So that two things matter: the shape of the paper and the pattern. So I don't know what will happen there.
Okay, so let's pump on the speaker of the morning.
Okay, thanks Massimo for chairing the session. We break for lunch and come back in